introduction. I'm honored to introduce my friend and colleague, invited speaker of this conference, Pedro Quaresma from Coimbra University. Pedro works in the area of automated theorem proving, automated reasoning, especially in geometry, and the area of internet accessible mathematical computation. He is the author of many essential publications of this research topic, each of which has shed light on important issues. I would also like to mention that Pedro, Professor Quaresma, is the creator of thousands of geometric problems for geometric theorem provers, a web-based library of geometry problems. It is one of the best contexts for testing and evaluating systems for mathematically proving geometric theorems. It is an essential tool for anyone working in research area of automated theorem proving in geometry. Finally, Pedro Quaresma is also the Deus ex machina of many international conferences and workshops in the field of automatic theorem proving. I only want to mention here that he is the creator of the group and conference TED, Components for Proving Theorems for Educational Software. This group aims to bring together the research community for theorem proving, automated theorem proving, interactive theorem proving, as well as computer algebra systems and dynamic geometry systems. This union aims to combine and concentrate systems from this area to improve existing educational software and study the design of the next generation of mechanized mechanical assistants. Well, today's lecture is entitled Automated Theorem Generation Finding in Geometry. Please join me in welcoming Pedro. And thank you, Pedro, for accepting our invitation. And you have the floor.
Thank you. I'm very pleased to be back to Urbino. I worked together for many years, and I came here to Urbino at least the second time, yeah. And you came to Coimbra also several times. So this is the today presentation is in two parts. The two parts are related to our work. The first is something that I presented, automated ADG, automated deduction in geometry, a conference of this area that took place in Belgrade, Serbia, in the last September. And the paper that is related to this presentation will be very soon available in Electronics Proceeding Theoretical Computer Science. I'm the editor of this volume, and it is almost done. So I hope that next week or something it will be available. So considerations on approach and metrics in automated theorem generation finding. Pedro Quaresma, Pierluigi Graziani, Stefano Nicoletti. And others, you will see. This is related to the 31st problem of Larry Woos, or was, I don't know how to pronounce this name. He, at a certain point, wrote a book about 33 basic research problems. And one of the problems he pointed out was to go from automated theorem provers, programs that were already very well established at that moment that prove conjectures, to programs that can find theorems and can decide to discover new theorems and to select interesting theorems. So these are two big issues. First, to discover new theorems, and the second, to filter the non-interesting theorems among them. You can, and I will present a potpourri of some researchers in this area, but you can generate new theorems in different ways. One of them that is very established in geometry are the inductive approach. The inductive is very well represented in something that maybe you already hear about, the dynamic geometry system. The GeoGebra, Cabri, those programs are very interesting because they are not CAD programs. They don't build fixed designs, fixed figures, but they construct geometric constructions, meaning that you define, for instance, 2 points. And from these 2 points, there is a theorem that says, an axiom that says that from 2 points, you can build a line. So you can build a line saying that object is tied to those 2 points. And you can build a new line saying that the line is parallel for the first. And all the construction is not fixed in terms of coordinates, it's movable, it's dynamic. And so it's very easy for a student, teacher, whatever, to build, for instance, a construction of Pappus theorem to parallel lines and lines connecting those lines, and saying that the connections meant at a line. And you move the whole construction, and okay, you see that the line, the 3 dots, the 3 points are in a line. Okay, it's a theorem. Let's say that it's a theorem. Okay, but this method is completely unsound. Not only our eyes sometimes fool us, but also the question of non-degeneracy conditions are completely overlooked. So this is very interesting, but from the point of view of automated theorem generation, it has a big drawback that the things that are created are unsound. So there are other approaches. I will introduce these two in one stroke. The generative and manipulative. These are theorem solutions or computer solutions. In terms of the generative, mechanically manipulation of symbols. One of the DGSs as a theorem prover that is a bit like based on this approach, not exactly, but the Cinderella as a probabilistic prover. It means that from a construction, he generates thousands of variations. And if in all those variations the conjecture holds, then with a high probability, it is a theorem. It can be calculated. And without going to that, these manipulation of symbols are something that we have a construction that manipulate this and this and this, and try to see if something holds. Again, is unsound. A different approach is the manipulative, generate conjectures from existing theorems. For instance, I remember that one paper they tried to apply generalization techniques from a theorem. Let's try to generalize it using different techniques. It is if the manipulations are satisfiability preserving, it is sound. Meaning that we begin with a theorem and manipulating it. If when the manipulations are satisfiability preserving, then the result is a theorem. The problem is that we obtain more of the same. We began with a theorem, and we obtain only variations of that theorem. Most of the times is if not every time, is uninteresting. So the most promising approach is the deductive approach. Application of sound inference rules to axioms. It is sound, and in geometry, we are more or less safe of infinity generation of results from initial set. From the axioms and from the construction, we have a finite set of possibilities, because this deductive approach in other areas has the problem of exploding the subspace and being completely unable to control that explosion of the cadence. Even in geometry, that's the problem, one big problem. But okay, at least it generates sound, and it can be. It can happen that the things that this method generate are interesting consequences of that construction. For a given construction with parallel lines and perpendicular lines and with angles, we can reach the conclusion that 3 or 4 points are with a property. For instance, Euler line is it is not clear in the beginning that the three centers, the several centers of of a triangle met in a line. Okay, this we can begin with a triangle with the construction of the centers, and for one, and this kind of approach would say that okay, these three dots, the 3 points are collinear, and it can be interesting. So by going in this approach, first more to the point approach was proposed by a researcher, saying that saturation-based automated theorem proofs, meaning that going to vampire or other automated theorem proof are well established, we can use these systems to try to generate logical consequences. Of course, they are sound. The problem is to avoid uninteresting logical consequences. Another approach presented by Sheng, Sheng, I think it's not an error, the two Shengs, but maybe, I don't know. And then pursued by Gao was the use of strong relevant logic based and using forward deduction reasoning. They follow this approach, applying it to several domains. Task is geometry, I will present a bit more later. Piano's arithmetic, and Shao worked on this for a couple of years. I don't saw any more paper about this from Gao. Maybe he is now working in other directions. Also in this deductive approach, one approach is implemented in a system, the GGEX, that implements the method proposed by Shu and others, and implemented by Ye, using a breadth first forward chaining based in deductive databases techniques. And they were able to obtain, to build a program, and we already, myself and a PhD student, we already implemented a new open source implementation of this method to reach a fixed point. the fixed point having all the consequences that we can infer from a given set of axioms and inference rules and a given construction. So, for instance, this is a screenshot of GGEX. GGEX is unfortunately for the moment discontinued. The original authors stopped working on it. There are now approaches to resume that work, but GGEX was and is very interesting in the aspect of combining the DGS and the ATP, the automated theorem provers for once, and the dynamic geometry system for the other. You can see on the right, there is the construction, the geometric construction that is the dynamic construction. Any point or any of, I don't know if you can see the points. Okay, you can see it's not very clear, but this point, okay, well, there are points red and there are points gray. Red points and red points. The red points are free points. They can move anywhere. The greenish, grayish points are fixed because they are obtained by the intersection of lines or other means. So, for instance, this H is completely fixed. And okay, for once we can use inductive reasoning, moving the points to see if something's hold. But for the other, we can use automated theorem prover based on the database method to say that this is true. Okay, I didn't show here the proof that this GTD prover used, but I show here the fixed point. So for this construction, this method finds 6 parallel lines, 12 perpendicular lines, 4 circles, 78 congruent angles, and so on and so on and so on. Of course, some of these results may be completely uninteresting. That's another thing, okay? But this method is efficient and from a set of axioms and inference rules and the construction can generate all the consequences that we can see from, can obtain from this construction. There are also other researchers working in terms of algebraic approaches. For instance, a well-known program, GeoGebra, has a version now, GeoGebra Discovery, and they use a fixed set of possibilities of properties, for instance, perpendicular lines, equal long segments, collinearity, and they will check algebraic. This is not symbolic manipulation like the other in GGEX, but nevertheless there are this kind of generation of new knowledge is something that is being pursued by many people in the area. In terms of the deductive approach, we can say that the general algorithm is like this. So from a set of axioms and the construction, we build a new fact list, the construction, and then if a new fact exists, we apply deduction and generate a new fact up to the moment that there are no new facts. The part of the filtering, we will speak of it in a moment. So, filtering. How can we address the problem of separate the good theorems from the non-interesting theorems. These filters that I will present are the more or less the combination of several articles about these and are completely speculative in nature. So the authors, in many cases, very close related to the method, to the program they use, speculate that the interestingness of a theorem can be obtained looking for some measures they more or less invented without any kind of validation. And they speak about obviousness, the number of inference in its derivation. Weight, the effort required to read a formula. This is very fluid sometimes. And some of these are very fluid. Complexity, the effort required to understand the formula. Surprisingness, measures new relationship between concepts and properties. Intensity, adaptivity, focus, usefulness. Some of these seems more reasonable, others more fluid. But the question is that in all the papers I read, they didn't try to, or they didn't build this on top of anything. Okay, we have this program. Let's see how using this program, this method, how can I find interesting problems? And they are very speculative. So, for instance, the AGINT system. I discovered that I had one thing strange here, and I forgot what it was. Okay. AGINT system described by Puzzles and others in 2006, they based the system. Remember the algorithm that I present in what they call the set of support. So the set of support is something that the automated theorem prover use to applying the axioms and the inference rule to derive other consequences. The set of support for at the beginning are the axioms and the constraint. And then applying a couple of filters to try to generate new theorems. The new theorems will be included in the set of support, and the old theorems are more or less discarded to the side. The things they build the filters on are, as I told, the kind of thing that I already told, but very related to the automated theorem prover they use. So they speak about the number of inferences, the number of symbols, the number of distinct functions and predicate symbols. So some of the measures, some of these are measurable, okay, can be counted, but for the reading the article, these are not easy to generalize to have a notion of interestingness that is not related to the program they build. The same with Gao. He speak about excavating abstract theorems. This is an approach a bit more like the manipulative approach, having a result abstracting from these. Again, degree of logical connectives in empirical theorems, proportional schema of formulas, something that are the problem I think in these approaches is that they are speculative for first, and second, they are very close to the method or the program they were using. So the things are not very easy to apply in other contexts. Colton described a series of programs and try to, in certain sense, summarize what they did, but these are systems more or less already a bit old. Okay, we reach a point that can we expect it to have a program for this issue, for this a program for this problem? And the thing that we proved is that it is not possible to have a program to find interesting problems. A program that is deterministic. Because by application of the Rice theorem, for any given Turing machine, it is undecidable to determine whether the language recognized by it as the property of finding interesting theorems. We apply Rice theorem and say, okay, the language, the property of finding interesting theorems is non-trivial, so we cannot build a Turing machine to this issue to solve this problem. So at best, this is a task to be addressed by programs based on algorithm guided by heuristics criteria. It was, in certain sense, the thing they already concluded, because they were proposing one and other fluid heuristic criteria. The question is that, okay, don't look what the new result or our result says is that don't fight this problem. It is impossible to have a deterministic machine to solve it. So we have to have some heuristics. But our proposal is to do not try this with something that myself and Pierluigi think in afternoon with some beers on the side, but to try to see this a bit more seriously. And we reach the point where we agree that an empirical exploration of the notion of interestingness is necessary. So, with a little help from our friends, we propose to have a survey asking the community to help us to reach the definition or at least some concrete characterization of the definition of interesting. And we developed a survey that is in that very long link. And we have already some answers. We began to analyze. One of the reasons that I'm here is to analyze that and to see the next steps. Some situations in which they remember to use the adjective interesting concerning a theorem. List several geometric theorems they find interesting. List several geometric theorems they find not interesting. We have to analyze the for now set of answers. We have to, we have many friends, but they are all very busy persons. So we have to pound a bit more to have more answers. But they began to look interesting. and I think we can be optimistic at this point. Small optimism, but I think we will gain a bit more from this. We will try to have some sort of measurement. We will ask these experts whether they find the theorem listed interesting or not. We'll ask them to rate using a Likert scale. This is a process that is more or less standard for you have already replied to questions in this Likert scale, from strong disagree to strongly agree. Is theorem and interesting? These kind of theorems found in the first survey. Why? Because it has the characteristics found in the first survey, and try to have a more scalable or measurable idea of this. And in last, with an argument of what an interesting theorem is, we could acquire experts in theorem generators, finders. We are not a huge community, and I'm almost sure that knowing them all, or almost all. So we will try to build such a program able to produce these interesting theorems. Okay, we are in the process. This is the first part. We already have the first survey. We are analyzing the first survey, and then we will go to the second and try to reach the point where we can have, I will not say completely define strict definition of interesting, but at least some notion that can be used by a heuristic program to generate and separate the uninteresting from the interesting, or the other way around. Okay. Then now I jump to something that is on the line of the thing that I said, but is more generic in certain sense, because we want also to work on the simplicity, readability, and interestingness of automatically generated proofs in geometry. This is, we are working on a submission to a Portuguese research project. FCT is a Foundation for Science and Technology, a Portuguese founding agency, the official founding agency for science in Portugal. And we are working also with Reinhard Kahl from the new University of Lisbon. I don't know if his name is correct because they call it Nova, but Nova is in Portuguese. I'm pretty sure that the new university is not approved translation. So, okay, I put it here, but with a grain of salt. I think it's the Nova University of Lisbon. Nova is new in Portuguese. And these three things are very important in geometry. Namely, the readability of a proof is very important when we go to education. We have, in terms of education, the dynamic geometry systems already established. Okay, in school, you expect not to have any kind of these big compass and rulers that we have in the past. Maybe you don't have even already that experience. You are expected to have the dynamic geometry system. But we are now pushing, okay, but these are unsound. how can we introduce the sound ATP part for geometry to be able to let a student to make a construction, reach a point where he can have a conjecture, and then call the automated theorem prover and convince, and that's the problem, convince the student that the thing that we produce is a proof of that conjecture. And this is the readability of a proof. Okay, I have with a colleague, Serbian colleague already a program, the GCLC that produces the proof. Sometimes is 1-2 pages small proof, others. I remember one that even LITEC was unable to compile the proof because it was something like 200 pages long, and at a certain point, the LITEC internals burst because they didn't support more and more and more and more thing. It was not the question of 200 pages, it was the question of symbols, different symbols, and okay, not even LITEC, and of course, many of those proofs are unreadable. And even a worse problem is that you cannot present formal proof to a high school, middle school student. You have to produce proof with many lemmas without forgetting all the steps needed by a theorem prover. And this is related to simplicity. Application of Ock and Razor say that the best proof is the simplest proof. And this, if you want to present a proof to a student, also you should have the simplest proof of possible. And of course, for educational purposes also, it will be interesting to, given a situation, to generate other theorems, interesting ones. So these things are related, and in this, one thing, if someone better than myself can have an idea for an acronymus, better one, this is horrible, but I'm horrible in terms of acronyms. So if you find some acronyms for simplicity, the readability of interestedness, please. Okay, continuing. So this is built on work that the group already produced. For instance, Reinhard Kahl, Ines Hippolyte, and Reinhard Kahl were the editors of the notion of simple proof, the Hilbert 24th problem. We will speak about that in a second or two. Myself, Pierluigi, and Stefano, the paper I already mentioned. Myself and Pierluigi also measuring the readability of geometric proofs, the area method case. So here we already try to have a measure of readability. And this is a paper in the Journal of Automated Reasoning, the journal of the area. It is a very good journal. Also with Van der Sant, Janun Baeta, taxonomy of geometric problems, and with Vanda, geometrography in dynamic geometry. This is education-related International Journal of Technology in Mathematics Education. We have other papers related to this, and the question of simplicity came from the Hilbert, the 24th problem. You know that Hilbert presented 23. But it was his intention to have a 24, and that problem was discovered in a notebook, a Hilbert notebook in the bibliothèque of Göttingen. And the problem says about the criteria of simplicity. We already took this in the area of geometry because Emile Lemoine in that area, and maybe influenced by Hilbert, proposed the geometrography. The geometrography was geometry, metrography, so measurement, and it has a measurement of the difficulty, of the simplicity of a given construction. Our paper is the extension of that for theorem provers. In a very using a specific theorem prover, but this is something that Cal and work in the more generic setting. We work on a more specific setting in terms of geometry, and is a theory of the method of proof in mathematics in general. Under a given set of conditions, there can be one simplest proof. And for geometry, we have already some very interesting results, and we want to, a first goal of the project, go from simplicity to readability. So check whether the analysis of the simplicity and readability of the geometry are complete or whether something has been overlooked. Answering the question requires not only empirical studies to understand what workers in the world of mathematics mean by simplicity and readability. This is also something that is not strict. Something is readable by one and not readable by other. For instance, my work with Wanda Santos is very connected with readability in high school, in education. So this project has a first goal going from simplicity to readability, and the second goal from the readability to intrinsicness, also the connection in the first part of this talk. Check whether the formal tools introduced to study the simplicity and readability of the geometric proof can be extended to describe the characteristics that make a theorem interesting and make such interestingness explorable from the point of view of automated theorem proving and finding in geometry. This is a project that will be submitted to FCT. Is as normal. It cannot be approved, but it will be also a line of research that we'll pursue nevertheless, if it is approved or not. Of course, if it is approved, it will be much simpler. We will have some help and more money to collaborate, but it will be something that we'll explore. So going back, simplicity, readability, and interestingness are these 3 points that we are exploring. And the last contribution was about the interestingness, but we have also some work about the readability and about the simplicity, and we will try to work together to find a better approach, better solutions to this. And okay, obrigado.